Hey everyone, on this lecture we are going to study the average degree connectivity measure in a network and in a graph. So we define formally the average degree connectivity as the average nearest neighbor degree of nodes with degree k. So to understand this definition and this measure, we are going to work with an example, and we are going to break down step by step how to compute the average degree connectivity, and finally we are going to do this with NetworkX. Now, first of all, to compute the average degree connectivity, first of all, we compute the degree of each node in the graph. Remember that the degree of a node is the number of connections that it has, the number of edges connected to this node. Step 2. For each node in the graph, we calculate the average degree connectivity by following these steps. First step, we get the degree of the node. B. We find all neighbors of this node. C. We compute the sum of the degrees of the neighbors, and finally we divide the sum by the degree of this node to get the average degree connectivity. And finally, the last step, we calculate the average degree connectivity for each degree value in the graph. So we aggregate all of the results across the nodes with the same degree. So to understand this and how we can compute the average degree connectivity step by step in an easy way, let us consider the following graph. It is a graph that, as we can see, it has 8 nodes. And so here, if we compute the average degree connectivity for each degree value in this graph, the solution is this one. For the degree 2, we have an average degree connectivity of 3. For the degree 3, we have an average degree connectivity of 2.333 and so on. And for the degree 1, we have an average degree connectivity of 3. But why? Well, let's justify why this is the solution. Let's compute step by step the average degree connectivity in this graph. So let's begin by studying the average degree connectivity for the degree 3. Okay, so how can we get this value 2.3333 and so on? So to do this, we need to study all of the nodes that have degree 3. Okay, so first of all, let's identify these nodes. We can see that the nodes that have degree 3 is first of all the node 7. The degree of the node 7 is 3. Also, we need to identify more. So 4, for instance, is also a node that has degree 3. 2 is also a node that has degree 3. And finally, the node 3. This is also a node that has degree 3. So this is the first step. We need to identify all of the nodes that have this degree where we want to compute the average degree connectivity of. So degree 3, we have here 4 nodes that have degree 3. So what we need to do is we need to compute the average degree connectivity of 7, the average degree connectivity of 4, the average degree connectivity of 3, and then the average degree connectivity of 2. And then we compute the mean of all of them, the average, and so we get this value. So let's begin with 7. So for 7, we need to compute here the degrees of the neighbors of 7, right? So the degree of 6 is 1, right? And the degree of 8 is also 1. And finally, the last neighbor of 7 is 5, and the degree of 5 is 2. Okay, so if this is the sum of all of the degrees of the neighbors, how many neighbors we have? We have 3 neighbors, 6, 8, and 5. So we need to divide this value by 3. And so if we compute this gives us 4 divided by 3, which is 1.3 periodic. So this is the average degree connectivity for this node 7. Let's now go to the node 4, which is another node that has degree 3. And let's also mark 7 as already done, already completed. So now let's go to 4. Okay, we need to compute the degrees of the neighbors. So first of all, the degree of the neighbor 5 is 2. Okay, the degree of 5 is 2. Then we compute the degree of the neighbor 3. So the degree of 3 is 3. Then the degree of the neighbor 2 is also 3, because the degree of 2, as we can see, is 3. It has 3 connections, 3 edges. And we are done because 4 has no more neighbors. So since we have 3 different neighbors, we divide this value by 3. So this gives us 8 divided by 3, which is 2.6 periodic. So with this, we complete the average degree connectivity of the node 4. So let's mark it as completed. Now we need 2 more nodes because they have degree 3 also. So let's go to 3 now. So let's begin with the neighbor 1. The neighbor 1 has degree 2. Then the neighbor 2 has degree 3. And finally, the neighbor 4 has degree 3 also. So with this we are done. We have no more neighbors. So now if we compute this, we need to divide this by 3, since we have 3 neighbors, and so this gives us, once again, 2.6 periodic. We mark the node 3 as visited. And now finally, the last node that also has degree 3 is the node 2. So now we study the degree of the neighbors of this node 2. First of all, the neighbor 1 has a degree of 2, so we here begin with 2. Now we continue the sum. We consider now the neighbor 3. This has a degree of 3. So here we add 3, and finally we consider 4, also with a degree of 3, and we add 3. With this we compute the summation of the degrees of the neighbors, and now we need to divide this by 3 because we have 3 neighbors. With this we get the average neighbor degree, and so we mark the last node also as visited. Very well. Once we have completed the computation of the average degree connectivity of all of the nodes of degree 3, we now compute the average of all of them. How many we have? We have 1, 2, 3, 4 nodes. So we here sum all of these values and we divide by 4. So once we compute the summation of all of them and we divide by 4, what we have? Well, we have as a result precisely the value 2.3 periodic that we saw at the very beginning as the solution. So this is how we compute the average degree connectivity by degree in a given graph. As we can see, it is very simple. It is merely a mechanical process, and the same steps we follow with the nodes with degree 1 and with the nodes of degree 2. So at the end we are going to end up having 3 and 3. Very well. So once we understand this concept of average degree connectivity and how to compute it formally, let's now see how we can implement this, and also how we can compute this value, this measure, given a graph in NetworkX, and also how we can implement ourselves a function, a process to compute this measure. So let's open a new notebook, a new Google Colab notebook. Let's add here a new text section to be the average degree connectivity. So now let's verify that if we have this graph, we can compute the average degree connectivity. In NetworkX, we have a function to compute the average degree connectivity on a given graph. So let's verify that when we use it, we have the same result. First of all, let's create this graph. So first of all, we define a graph G. We begin with an empty graph. Also in this notebook, we are going to need the NetworkX library and also the PyPlot module from Matplotlib to draw all of the plots. So make sure you import both of these libraries. So now let's add the nodes to this graph. Here you can see that we have the nodes from 1 to 8. We can add these nodes with the function add nodes from, and we pass this in format of a list, 1, 2, 3 until the node 8. The same we can do for the edges. So here we have the method add edges from. We pass these edges as a list. The first one we can see, for instance, 1, 2. Here we have 1, 2. We also have 1, 3. So here we pass all of the edges in this graph. This is something we already know. So apart from computing the average degree connectivity, we can also visualize this graph. So we are also going to plot it. So we are going to draw this graph G, and we want to identify which are the nodes. So I want to identify this is the node 1, this is the node 3, this is the node 8, and so on. So we have here the argument with labels that we are going to set this argument to true to label the nodes. So here we can compute very easily the average degree connectivity with a predefined function in NetworkX, and here with the name average degree connectivity, that given a graph G, it computes the average degree connectivity by degree, the same that we did formally before. So now, once we have this, we can print these results. Note also that this function returns the dictionary where the keys are the degrees and the value, the average connectivity. So we need here to print all of the dictionary, we need to traverse this dictionary. So for each key in the dictionary, which is the degree, and for each value, which is the connectivity, in all of the items of this dictionary. So here we can use the name of this dictionary with the items method that returns all of the tuples key value that belong to this dictionary. Essentially all of the items, all of the elements of this dictionary. We can here print the value of the degree and its connectivity, and we can print this with an F string. Remember that an F string is a string where we can insert inside the same int string literal expressions, right? these expressions can be inserted between braces. So here we can type something like degree, and here we can insert this variable degree, this key degree. Note how we insert this with these braces, right? Bear in mind that this is only possible if we type an F before the string. This is what an F string is in Python. Here we keep writing, this is 2 points, and here we can type the average degree connectivity equal, and here we can insert once again between braces the expression connectivity, right? This value connectivity for this given key. Very well, so with this we have everything. We can now run this window, we can now run this cell, and we're going to visualize this graph and also the average degree connectivity of all of the degrees. Okay, so we also here need to verify that we have the same results. So let's run this cell. Very well, so here as we can see, here is the graph that we have. Okay, this graph is the same that the one that we are given. And here we can see how the average degree connectivity for all of these 3 degrees of difference that we have are precisely the same values that we computed. The ones that we discussed before. Right, so we are able to do this with this function. Now, this is a predefined function, okay, in NetworkX. So imagine we don't have this function. How could we compute the same thing, the average degree connectivity by degree, on a given graph, given a graph G? Well, we can do it this also. We can implement an algorithm to do this because we already know the steps that need to be taken to compute these values. So we're capable to define an algorithm to do so. So here let's add a new text section. Let's name this section to be implementation of the average degree connectivity. And so now we're going to begin with the same graph here. So we can copy this and paste it in here. The graph is going to be the same, but now we are not going to use this predefined function of NetworkX. We are going to compute it ourselves. Now, to implement this algorithm, to compute this measure, it is very important to remember these steps and everything that we've done before, since we are going to capture all of these ideas in the algorithm. So here, let's first of all compute the degree of each node. So to do this, let's first of all define a dictionary for the degrees. We can get this with a dictionary constructor in Python, and here we are going to access the degree of the graph. This is going to return a mapping between nodes and the degree. So we're going to have here dictionary where the keys are the nodes and the values their degree. So now, first thing, we need to compute the average degree connectivity for each node. Okay, and then we classify the ones that we want. The ones that have degree 3, we compute the average of them. The ones that have this degree 2, we compute the average of them. The ones that have, finally, degree 1, we compute the average of them. So now let's compute the average degree connectivity for each node. So at the beginning, this is going to be an empty dictionary. So here the degree connectivity is going to be an empty dictionary at the very beginning. And now here for each node in the set of nodes of this graph, we are going to access the degree of this node. So we access the degrees dictionary with this key. Remember that this degrees is a dictionary, it is a mapping where the keys are the nodes and the values are degrees. So when we type something like this is returning the degree of this particular node. We also need to access the neighbors of this particular node. So in NetworkX, if I have a graph G, we can access the attribute neighbors for a particular node, passing this node as an argument. So once we have the degree of this node, I have the neighbors of this node, I also need the degree of the neighbors. So let's define the neighbors degree. Since we are going to here compute multiple degrees, let's name this neighbors degrees. This is going to be a list, of course. We can define this list as a comprehension list. So the idea is that we are going to here insert in this list the degree of this neighbor for all neighbor in the list of neighbors, which is here this one. So for all neighbor in neighbors. So what we're doing here essentially is we're putting inside this list all of the degrees of the neighbors, right? For all neighbor that belong to the list of neighbors of this particular node. Very well, so with this we have already all of the information that we need to compute the average degree connectivity of this particular node. So the average degree connectivity of this given node, remember that this is a dictionary. So we are going to now define the value for this key in the dictionary. The value is going to be equal to the sum of all of the neighbor degrees, right? So neighbor degrees divided by what? Divided by the degree of this node. And so what is the degree of this node? Remember, the degree of this node, for instance, is the number of neighbors. That's why here what we do is, once we have the sum of the degree of all of the neighbors, we divide this by the number of neighbors, which is precisely the degree of the node. So what we are doing right now is doing this computation in here. This is the sum of all of the degrees of the neighbors, and now we are dividing by the degree of this particular node. And this gives us the value that we are saving inside the dictionary. Very well, so with this, we have the average degree connectivity for each node, right? Now, what we want at the end is the average degree connectivity defined by degree, as we can see in here, what we did. And this is precisely what we do with the average degree connectivity of the NetworkX function. So let's do the same thing. Is this hard? Of course not. So because once we have the average degree connectivity for each node, we can easily calculate the average degree connectivity for each different degree value inside the graph. We only need here to define an empty dictionary initially. So let's name this degree connectivity dictionary. So let's just here use dict. Initially, of course, is going to be empty. At the end, what this is going to have is a mapping, is a dictionary that the keys are going to be the degrees and the values, the average degree connectivity, right, for this particular degree. So now what we need to traverse, we only need to traverse here this dictionary, the one that we already completed inside this loop, inside this for loop. Now we traverse this dictionary. So for all node, right, and their particular connectivity, so for all key and value inside this dictionary in here, so in the average degree connectivity item, so we can here copy this dictionary and we use the method items to get all of the elements. Remember that these items returns the tuples, okay, key value pairs that belong to this dictionary. So first of all, we get the degree of this node. We can do this with degrees for this particular node. Remember that the degrees is a dictionary that given a node, okay, which is the key, tells us the value, which is the degree, this degree of this particular node. And now, if this degree is a new degree, we specify that the degree and the average degree connectivity of this particular degree is this one, is this result. And if this degree is not a new degree, we need to append it. Okay, we need to append it onto the dictionary, so that at the end we can compute the summation of all and calculate the average, which is precisely what we do here at the end, right? Once we have of all, this particular case for the degree 3, once we have the values of all of the degree 3, we make the sum of all of them and we divide by 4, which is the number of nodes of this particular degree. And this gives us the final value that we want, right? This gives us the final solution for this particular degree 3. So we check if this degree is inside the dictionary that we are here using of degrees, then what we are going to do is we are going to append in this degree connectivity dictionary, we are going to append, we are going to do this for this particular degree, for this particular key, we are going to append this value in here, right, the connectivity, which is the value for this particular key. Otherwise, if this degree is a new degree, then we just set the degree connectivity dictionary to have precisely this value, connectivity, of course as a format of a list, because it may happen that we need to add more values, so we at the end compute the summation, so we set this to be a list, not a real value, a list of real values, right? Notice how if we only have a real value, we cannot append another real value to an existing real value, but if we have a list, okay, with one real value, of course, we can append another real value to this list, by definition of list. Very well, so with this we have, for each different degree in the graph, we have a list containing these values, okay, the values that we want to compute the summation of, and then compute the division, so we get the final value, right? For this particular case, this is the case for the degree 3, but what we have inside this dictionary is for each different degree, the list of values that we need to compute the sum and finally make the division. So now finally, let's compute the average degree connectivity for each degree value. So initially we set the average degree connectivity dictionary to be equal to an empty dictionary. And now for each degree and connectivity values, which is going to be a given list, right, of connectivity values for a particular degree. in this dictionary in here, in the degree connectivity dictionary, so in these dictionary items, remember that this dictionary, what we have is, it is a dictionary where the keys are degrees and the values are lists. So what we have is, for each degree, we have a list of the connectivities that we need to compute the sum of, right? And then make the division. So very important here to bear in mind, this is very important. Bear in mind that in this dictionary, the keys are degrees, are integers, and the values are lists. The values of this dictionary are lists. For each key, we have a list, right? Very important. So for each degree and list connectivity values, the respective list for this given degree, what we're going to do? Well, we are going to trivially compute the average degree connectivity for this particular degree. So the average degree connectivity for this particular degree, what is going to be? Well, it is going to be the sum of this list, right? It's going to be the sum of this list. With this, we are computing this sum in here, in parentheses, okay, all of this sum. And now we need to divide by what? Well, by the number of different connectivities that we have. So in this case, we can get the length of the connectivity values, the length of this list. This is how we compute the average, right? Here, as we can see, we have 4 different values that we're making the sum of. So we divide by 4, we have 4 different values, and this gives us the final result. So this is precisely what we are formalizing here. We compute the sum of all of the elements in the list, and we divide by the number of elements in this list. And note that we are doing this for each different degree, okay, and list in this graph. So this is going to be done for all of the different degrees in this graph. Notice how we have this for loop. So we're going to do this for all of the different degrees. Very well. So with this, we have everything. Finally, we can print the average degree connectivity. So we can just print them. Notice how this is a dictionary, and we want to print all of the elements of this dictionary. We need to traverse this dictionary. So for each degree and connectivity in the elements of this dictionary, so we just copy this dictionary and we access the items of this dictionary, we are going to print inside an f string. So here we can use an f string. Remember that we use an f string here so we can insert variables, we can insert expressions inside this same string literal. Okay, we can insert them between braces. So here we can type degree. Now here we print the degree, the particular degree. Now 2 points, and here we indicate the average degree connectivity for this particular degree. So here we just said equal to the value that we have here, okay, this value in here. Notice that in this dictionary, average degree connectivity, the keys are degrees and the values are float values, are real values, okay? They are not lists, they are real values. On the other hand, this dictionary, degree connectivity that we have here, this dictionary, the keys are degrees and the values are lists. In this one, okay, that we are using now, the keys are the degrees and the values are real values, okay, are representing the final solution, the final connectivity, the final average degree connectivity for each different degree. Very well, so with this we have everything. We have everything implemented now. Here additionally we can also display this graph, so here we can just use the draw method from NetworkX. So we here are going to display the graph G, and we want to display the graph, and also we want to be able to identify the nodes, right? This is the node 1, this is the node 5, this is the node 8, and so on. So we here set the with labels argument to true. Okay, as we set this with labels argument to true, we are going to label all of the nodes, so we are going to identify them, right? So now we are printing the average degree connectivity for each degree in here, right? We are printing this average degree connectivity for each degree, and also we are plotting this graph, right? So as we have implemented this algorithm, we should see the same result as we saw before in here. Notice here that we are not using any NetworkX function to do this. We are doing ourselves, okay? It is our implementation. So let's run this window, let's run this cell, and verify that everything is working fine. So we run. Very well, and now as we can see, here we have precisely the same graph as we were given, and here we can see how the average degree connectivity for each degree is the same. Okay, we have precisely the same result. Also, remember that whenever we have a different execution, the drawing changes. Okay, this is by definition, and it is default, the default behavior in NetworkX. But note how the average degree connectivity is always the same. It is precisely the solution that we have. So this shows that the algorithm is correct, and we have implemented precisely an algorithm to compute, given a graph G, the average degree connectivity by degree. Once again, it is very important to know that in this algorithm, what we're doing is precisely the steps that we took at the very beginning and we discussed step by step. So this algorithm is precisely doing this. Okay, so we have implemented an algorithm to compute the average degree connectivity by degree in any graph that we can have. Very well, with this we end this lecture on the average degree connectivity. We remind the student, as always, that you can download all of this notebook and all of this code that we have used on this lecture, as well as the documentation on the downloadable documents of this lecture.